Hello, everyone. My name is Professor Victor Cheng. I'm very honored to give a talk on behalf of the team. The title is called An Improved Federated Learning Algorithm for Privacy Preserving in Cybertwin-Driven 6G System. And that is a paper that we have published on IEEE transactions on industrial informatics. And with the links here, why 6G? As you may have noticed that our technology has advanced. So 6G stands for sixth generation network for communication and network systems. Then 3G from 2000 and then 4G in 2010. As you notice that every 10 years there is a major advancement, and 5G in 2020 and 6G 2030, which also stands for Internet of Everything. That allows us to bring people, process, data and things to make 6G network connection more relevant and valuable. And how 6G works is that it works with super traffic, with smart industry, with the smart agriculture, with the medical industry and medical IoT, with the cyber twin, with the supply chain and finance and blockchain economy. So we live in an information age that there's always a vast improvement and in terms of volume and the amount of data being processed. And 6G network is very vital in a way that we can download a movie within seconds, and it is also used in the Russian invasion war in the way that when all the infrastructure have been destroyed, and then with the help of the 6G network, then the military from Ukraine can also receive the information without being affected. So 6G can have a massive impact in our life with the connections of everything, and we can know the updates in real time. And why Cybertwin? Cybertwin is a digital representation of humans or things in a virtual cyberspace, and it's located at the edge cloud. In a way, we can then see that 6G works closely with the Cybertwin to allow us to upload everything and get access to everything. Imagine this is a very large version of Apple Cloud or Amazon Cloud, and then you serve in multiple capacity, such as communication assistant, network data, logger, and digital asset owner, in a way that we have lots of interactions to move data and then retrieve the information from, and in somewhere that we work. However, it's not safe to upload the raw data to the Cybertwin, and in the process, it will also have the problems with the security and challenges for privacy. So, and that is the reason why we focus on this work, and we have three major contributions. As you can see, first of all, we employ a privacy-preserving collaborative learning framework in a Cybertwin-driven 6G, and they can bring the global machine learning model with the imbalanced data set in each client. The thing is that we work on the client to ensure that it does not have any imbalanced data set, so that we can work more efficiently and effectively. With this, second, we design an estimation scheme that can measure the class distribution of the selected client without awareness of the local raw data in client, in a way that it makes it more efficient, and then to work with a much better optimization and the outputs. And then we propose two online client selection algorithm. In short, they stand for CSCUCB and CSHE, and they can select the client subset with the most balanced data set for individual model uploading and aggregator model uploading, thereby improving the accuracy of the training model in federated learning. In this way, we can get these two algorithms to make the uploading very effectively with high percentage of accuracy, so that we then can allow everything to be working together. So federated learning may become one of the very important or highly crucial learning among AI. And how can we do this? There are three steps involved. First of all, the step one, the server broadcasts the global model to the selected client. Step two, each selected client performs the local updates and uploads the local model of the server. Step three, the server aggregates the received model. As you can see, it's very similar to this diagram. And you upload the local model there, and then at the same time, you then broadcast the the global model. And then what you do is that you only transmit the model, not the raw data, because when you transmit lots of raw data in between, first of all, the transmission rate may not be very high and is likely to get unsuccessful, and you may not get anything done. So you only transmit the model. In this way, we then can use the federated averaging to disseminate the updated model to the client. And in this process, we then can get a web of the services of the application, and then we can then exchange with the machine learning model with the server instead of the raw data. Then what we will do is that the imbalance, class imbalance in federated learning is an issue. Why? Because this exists and we could solve. So global class imbalance in overall data set, and then in the local data set, you have a local class imbalance. So as a result, we have these two issues to resolve. The training procedure in the deep neural network in federated learning become unstable, and the train model is biased towards the classifying the majority of classes data. As a result, we have to fix this two issues for federated learning for both the global class imbalance and the local class imbalance. Then how do we do this? Because we always need to propose the solution for it. And the way we do this is to have a callback labeler or KL divergence. So this divergence will allow us to improve the test accuracy by selecting the client set of the balanced data distribution in each route. And it's also to measure the imbalance level of each client. As you can see, that represents the uniform distribution to ensure that everything is uniform. Therefore, our objective is to select the client subset with the most balanced class distribution. So in this way, it allows us to do our selection carefully. So then we can get the most balanced one. And then the class estimation algorithm is an important thing. And how does it work is that, as you can see in this diagram, we can upload the model, and then we validate the data set with the balanced class distribution. The next step is that we have the gradients with respect to each class in validation data set, then to get the estimated class distribution. So the steps involved is that, first of all, it has the fit of the data sample of the validation data set. Then you have the, to calculate the validation loss with respect of each class and its corresponding gradients. The third step is we are going to normalize. And as you can see with this variable by the softmax function, and to obtain the estimated class distribution. Then with this variable, it represents the amount of the data participate in the training in the routing. So in this way, it allows us to know the size of the imbalanced validation data set is being in a good shape, so that we can then get a possibility. So in this way, we do things step by step. So based on the validation gradient, we estimate the proportion of the data sample for the class. So we then can look at this context more carefully. As you can know, the client selection of online learning framework, they've been done by a series of formula. Then we can translate them into algorithms step by step. So first of all, we need to know the awards of the client for every single thing you have done. Then we have the award for that. So then we then donate the time that the client K is selected. So the upload rule is being given by this. Then the average reward of the client K is updated by that. So every time you update the client K, and there's the average reward, and then the estimated class distribution of the client K is also updated by that. And then this variable represents the decay factor. So if things take too long, of course, there's a possibility to subject to the decay, and then with a decay average. So then we have to calculate for every major parameter. And then how does that work with the algorithm? In this case, we call that CSCUCB. It has a very long name that stands for client selection for CUCB. So this is the algorithm that looks like. And then one of the important processes called iterative client subset search. So how does it work is that, first of all, it then at the beginning of the round, we select the as clients, the round robin scheduling, and then update with the time, and then with all the key variable, with the formulas that is available on our paper. Then we then perform a for loop. Then when for every client, then we perform the task for that. So then we then have the iterative search. So the algorithm in this way it then checks. Of course, it needs to satisfy the requirement. And wow, there's a loop. Then we then get to the minimum one that match with the most balanced data set. Then once we find that, then we get the output, so that it then done. So this is a simple explanation for our CSCUCB algorithm, and if you can check our paper. So then when how do we actually meet aggregator model when uploading? And this is the case. In summary, in some scenario, the broadcast server could not receive the individual model, such as SEGEG. Then it is not available to employ CSCUCB algorithm for the federated learning, and that is the issue. And then it leads to us to think, how do we find the most balanced client subset for aggregator model uploading? Because it's not always the case you can find easily. So this is how it looks like. We upload it. So there's a secure server called SEGEG. Then they put to the broadcast server. Then in this way, this aggregator model. So this also works as a secure server to ensure that it has been kept up to date. And that's the thing that we then have to work with the aggregator model uploading. And to do this aggregator exploration with Hadamard matrix, how does it work is that for aggregator model uploading, the server only obtain the composite class distribution via the balanced validation data set. So it has been in the representation of 1 and -1. So when you have a representation 1, it means that yes, go ahead. But when you have -1, then you have to wait until the right time or the right criteria has been met. So the why Hadamard matrix is to help the efficiency estimate of the class distribution of each client. Imagine there can be different clients. Of course, there are different possibilities, and we have to make things more efficient. And of course, this matrix will help us to understand the status too. And the property of this matrix is that the entry of the first row H1. So at the beginning, yes, the first time will go. Then if let's say when the queue or the request has been in demand, then of course you will check if it exists with equal numbers or +1 and -1 entries, then it will go next. So the equal number, then it will go next. Yeah, if the equal number will go next. Then exploration of the aggregator model uploading. In this case, that we then can check this is the algorithm. We need to first explore the class distribution of each client. So in this way, you will see there's a good use of the loops. Yeah, and then we will select. Let's say if you are searching for certain things for m times, observe the class distribution for m time, then calculate the average output. Yeah, so then we then know what will be the output. And of course, then we then perform the Hadamard matrix. Yeah, so this condition will need to check the Hadamard matrix, and after that we then get to leverage the size of the entries in Hadamard to indicate the client selection. So once we then use the Hadamard then to identify the most suitable client selection. So then we then summarize the proposed CSHE algorithm by aggregator model uploading in federated learning. So how does it work? So CSHE is also the second important algorithm that we propose. So when all the major inputs, so then for the T, it goes into loop and obtain estimated class distribution of the Hadamard matrix. So we then use the Hadamard matrix as a way to help us to double check and to explore and exploit the algorithm. And for the client selection of aggregator model uploading in federated learning, so the algorithms can then balance exploration and exploitation and obtain the accurate estimation of the class distribution and select the client subset the most balanced class distribution. So then it then goes to that for the client K, calculate the upper bound. So then we can count what would be the upper bound. So because when the award is higher, then there's a higher possibility for you to go forward and to get a better match of the criteria. Then we select, yeah, so then we then use the ITER search, yeah, so the search criteria that also I presented earlier. Then we update the final one, and then we get it towards the end. So we had performed experiments as follows with a PyTorch with a GTX 1080 with a Ubuntu 16.04, a number of client 128, a number of selected client 32 data sets. We also explained the rationale of using those data sets on paper. The global class imbalance long tail distribution, and we have a local class imbalance. We use the distribution, and we have the number of samples in validation, just 32 samples, so we can then match with the 32 clients in a way there may be better match. But also we have a baseline, not only to test our own algorithm, but also we test with others, such as the greedy, such as the CSRE and MD cluster random, so that when we perform an experiment, not only to validate our own work to ensure there is a good performance evaluation, but also we compare with other similar methods, so to compare and then to see how far we go and how good or how ours our results will be. So just to summarize the model training performance, the performance of different algorithms with different individual model uploading. So as you can see, sometimes the differences are significant, sometimes the differences are so small. So the summary of our results showed that the proposed CSCUCB algorithm can increase the test accuracy, the 10%, as you can see, about 10% here compared to other methods, and about 4%, yeah, in another data set with a very tiny difference for the federated learning compared to the conventional model. So we have about 10% and 4% improvement in test accuracy. Then with the model training performance, with the aggregator model uploading, then with the communication round, and we have also better performances compared to others. And also we have a small improvement in terms of test accuracy compared to others. The proposed CSHE algorithm can efficiently find a balanced client subset, even with the aggregator model uploading. And then we then perform the different algorithms with different percentage of involved clients, so to test whether our model can work in such a way, because in reality you always work with multiple clients, and you will have concurrent tasks at the same time. So in comparison, our work CSCUCB has higher test accuracy compared to all other competitive models. And similarly, we also have a better test accuracy compared to other models. So the two algorithms are robust with different percentages involved with clients. So how do we achieve privacy? So as you can see, there are two ways to achieve privacy. First of all, the proposed algorithm works totally on the server. So that we do not require any client share for any extra information, and except on a local train model, because if we only search the one we need and only get to the model we need, so we don't have to get any extra computation, extra unnecessary resources. And then secondly, the proposed algorithm can combine with other type of privacy preserving in federated learning, such as the SEC, to further improve the security of the data privacy. So you can also work with other types of security solution to enhance the existing feature for our data privacy. So in a way, first of all, we only need to use the thing we look for, and they do not require to take a lot of time, and it's also having a good test accuracy, and secondly, works with other types of security and privacy solutions. So in conclusion, we propose and impose federated learning algorithm to protect the privacy of the Cybertwin-Driven 6G networks. So our two algorithms works to protect the privacy. And then we develop an online learning framework that could determine the class subset with a balanced class distribution from the available clients. So then we can then find a better search and then get to know all the client subset and to meet our criteria. So our simulation results show that the proposed algorithms can also significantly improve the performance of the model training for federated learning in Cybertwin-driven 6G networks. So we will really appreciate the time you listen. We hope that you can visit the website and to download the paper. And I hope that if our work is relevant to you or inspire you, please consider citing our paper, because citation is also an important thing, and we will need your support. And thank you so much for your consideration. We appreciate your time, and hopefully we will be able to do another presentation again. Thank you. Bye.